Welcome to the deep dive. Usually when we talk to you about a fundamental physics concept, there's this expectation of clean, clinical precision.
Oh, completely.
Oh,
You probably imagine a physicist standing next to a perfectly straight train track.
Right, holding a flawlessly synchronized flashlight and a stopwatch. The environment is a vacuum, the math is neat, and everything behaves exactly the way we expect it to.
It's the classic thought experiment. I mean, it's binary, it's contained, and it completely strips away the chaotic messiness of the real world, just so we can isolate a single variable.
But then you step into the world of really idiosyncratic, highly alternative physics models, and suddenly that perfectly straight train track just completely vanishes.
It really does.
Today, our mission on this deep dive is to explore a fascinating, just fiercely unconventional blog post by an author writing under the name Zionad 2023.
Yeah, Zionad 2023.
And to understand the fabric of space-time through their eyes, we are throwing out the sterile vacuums. Instead, we're going to be using the tactical formations of ancient Chinese generals,
Which is amazing.
the air pressure sensors on the nose of a modern airplane, and, of all things, the high chair of a Wimbledon center court tennis umpire.
It is a wild, incredibly visual ride. But before we get into the ancient generals or the aerodynamics, I actually need to jump in and set a crucial ground rule for our deep dive today.
Oh, yeah, absolutely. Go ahead.
The source material we're unpacking fundamentally challenges mainstream physics, specifically Albert Einstein's concepts of special relativity and the established idea of Lorentz contraction.
Right, the really big stuff.
Exactly. So I want to make it absolutely clear to you, the listener, that we are not endorsing these alternative theories as fact, nor are we taking sides against mainstream science.
We're just the messengers today.
Right. Our goal today is strictly impartial. We are stepping inside the author's deeply philosophical alternative framework to unpack their thought experiments. We just want to see exactly how they perceive the universe.
Okay, let's unpack this. Let's start with the very first analogy the author throws at us to break down our assumptions about reality. The airplane. Right, it's an airplane. We are told to imagine an airplane that is exactly 20 units long. And this airplane is trying to do something very basic, measure its own airspeed.
Right. And to calculate airspeed in real life, an airplane relies on different pressure sensors. The author places a sensor right at the very front tip of the nose.
Let's call that position on a grid x equals 20.
Perfect. So this front sensor is measuring what's called total pressure, which is basically the force of the air ramming directly into the plane.
Makes sense.
Then right in the middle of the plane at x equals 0, there's another sensor measuring static pressure, or just the ambient pressure of the air around it.
Okay, so we have the nose at 20, the middle at 0.
Right, but here's the catch. The computer that actually takes those two numbers and calculates the speed is located all the way at the back of the plane at x equals -10.
Which, sounds like a pretty standard engineering setup. You have sensors scattered around, wiring, routing back to a central hub.
Yeah, perfectly normal.
But the author points out a massive flaw in how we think about this data collection. We tend to think of information as instantaneous, and, well, it's not.
Exactly, and that is the core physical dilemma the author is raising here. I mean, radio waves or electric signals travel incredibly fast, but they still take time.
They aren't magic.
Right. When that front sensor at x equals 20 takes a pressure reading at exactly time 0, let's say t equals 0, it has to physically send that data down the length of the plane to the computer.
And that takes a minute or a fraction of a millisecond, really.
Exactly. By the time that signal finally travels those 30 units of distance and reaches the computer at the back, time has passed. Let's say it arrives at t equals 20.
Okay, I'm following.
But meanwhile, the middle sensor took a reading at t equals 10 and sent its signal. Because the middle sensor is closer to the computer, its data arrives at the exact same moment as the data from the front.
Oh, wow. So you end up with data from two entirely different moments in the past arriving at the computer at the exact same moment in the present. It's temporal chaos. If the computer just crunches the numbers the second they arrive, it's calculating an airspeed based on the nose of the plane from one moment and the middle of the plane from a completely different moment.
It would be a completely invalid calculation. The reality of the plane's speed gets distorted by the delay in the information.
It's like trying to watch a live sports game on TV while listening to the local radio broadcast.
Oh, that's a good way to look at it.
Yeah, the radio is usually a few seconds ahead, right? So you're hearing the announcer scream about a touchdown while the quarterback on your TV hasn't even thrown the ball yet.
Exactly. The signals are out of sync.
Right. So to get an accurate experience of what actually happened at the exact same time, you have to hit pause on your DVR for exactly 3 seconds so the visuals and the audio perfectly align. You have to artificially create a simultaneous now.
That is a brilliant analogy, and it's precisely what the airplane's computer has to do. The author explains that the computer uses what they call an abstract capacitor.
An abstract capacitor, like a battery.
Well, more like a memory buffer. It receives that early signal from the middle sensor and just, holds onto it.
Oh, I see.
It delays the data on purpose, storing it until the signal from the front of the plane finally catches up. The computer forces a simultaneous reality inside its own memory so it can do the math correctly.
But a single airplane is a closed, controlled system. We program that computer. How do you scale that up?
That's the big question.
Right. If you have multiple objects in the universe, all moving at different speeds, all experiencing their own unique information delays based on how far away they are from each other, how do we ever agree on a shared reality?
That is exactly the puzzle the author tries to solve next. And to visualize it, they map out the positions of different observers using historical figures from ancient China.
Which is such a unique way to frame a physics problem.
It really is. We have 3 main figures representing 3 entirely different viewpoints in physics.
First, we have Han Xin, who the author calls the Train King.
The Train King, yeah.
He is positioned on the floor of a moving train, hovering slightly above the ground at a height of z=10. Han Xin represents the standard observer sitting inside a moving system, what physicists call a moving inertial frame.
Then we have Xiaohe. He is completely stationary, standing outside on the train tracks at y=-10.
So he's just watching the train go by.
Exactly. His job is to observe Han Xin's train moving past him and mathematically calculate its movement from the outside.
And finally, we have Lu Bang, who the author equates to a president or an umpire.
Right.
Lu Bang is positioned incredibly high above the action at a height of z=100, looking straight down at the flat plane where Han Xin and Xiaohe are operating.
What's fascinating here is the specific role Lu Bang plays. The author likens him to a center court umpire at Wimbledon.
Okay, a tennis umpire, how does that work?
Well, to judge a tennis match fairly, the umpire sits in that high chair and has to mentally erase their own physical location on the court.
Because they're physically closer to one side of the net than the other.
Yep. Right. They have to ignore the fact that they are physically closer to player 1 than player 2, which means the sound of the racket hitting the ball reaches their ears at slightly different times depending on who is serving.
Ah, the delay again.
Exactly. Lu Bang, high up at z=100, is receiving delayed, chaotic light signals from Han Xin on the train and Xiaohe on the tracks.
Because it takes time for the light bouncing off the train to reach his eyes way up in the sky?
Precisely. But because he is elevated, acting as the absolute umpire, he applies a mathematical correction. The author says Lu Bang uses a complex space, specifically applying a time depth of t=-1.
Okay, wait. Let's break down that math for a second, because t=-1 sounds like time travel. What does the author actually mean by that?
Think of t=-1 as the mathematical equivalent of rewinding the tape.
Rewinding the tape. Okay.
If Lu Bang sees an event happen on the tracks, and he knows based on the distance that the light took exactly 1 second to reach his eye, he applies a -1 second modifier to that data point.
He shifts it backward in time in his own logs.
Right. He isn't physically changing the universe. He's correcting his own delayed perception to plot the event precisely when and where it actually occurred in absolute space.
Oh, so he reconstructs a perfectly fair, simultaneous historical map on a clean Cartesian coordinate system.
Exactly.
Wait, let me challenge that for a second. Einstein's whole model of special relativity, the entire concept of space-time intervals, already accounts for the time it takes light to travel between observers.
It does.
That's literally the foundation of a space-time diagram. Why is this author claiming mainstream physics forgot about the delay when delay is mathematically baked into relativity?
It's a great point, and it cuts right to the heart of the author's critique. The author isn't saying Einstein forgot that light takes time to travel. The critique is about how mainstream physics interprets the result of that delay.
Okay, how so?
Mainstream relativity says that because the speed of light is constant for everyone, time and space themselves are relative. It says space physically warps and time physically slows down depending on your frame of reference.
Right, the bending of space-time.
But the author argues that this is mistaking a mathematical model for physical reality. They believe physicists became so obsessed with the math of the Cartesian grid that they started believing space itself squishes.
Wow. So the author's saying, no, space isn't squishing. You just forgot you need an umpire to correct the delayed data.
Exactly. You're confusing the optical illusion of delay with physical reality.
So to have a fair umpire, you need an absolute unmoving court for them to judge on. I mean, Wimbledon doesn't work if the grass itself is sliding around while the players are running.
But that would be a terrible match.
What is the court in this author's universe? If it's not relative space-time, what is the absolute background?
According to the source, the absolute court is Maxwell's electromagnetic field, the EM field.
The EM field is the tennis court.
Yes. The author treats the electromagnetic field as a real, physical, non-material reference frame that spans the entire universe.
And they ground this in some very specific historical experiments to prove the field exists. They bring up Ole Römer, the 17th century astronomer who first measured the speed of light by watching the eclipses of Jupiter's moon, Io.
A classic experiment.
And they bring up James Bradley, who measured the Earth's orbital speed by slightly tilting his telescope to catch starlight, a phenomenon called stellar aberration.
Right.
Think of running in the rain. You have to tilt your umbrella forward because you are moving into the falling raindrops. Bradley realized we have to tilt our telescopes because the Earth is moving into the falling rain of starlight.
Yes, and the author uses those historical measurements to introduce a foundational concept they call velocity alpha.
Velocity alpha, okay.
This is where their model wildly diverges from standard physics. Mainstream physics might say, the Earth is moving around the sun at about 1/10,000th the speed of light. Yeah. But the author says, hold on. That's just the Earth's speed relative to the sun. What if the sun itself and the entire Milky Way galaxy is also moving through this absolute invisible EM field?
Oh, they are moving at velocity alpha.
Exactly. Let's say you're on a train walking forward at 3 miles per hour. To someone inside the train, your speed is 3. But if the train itself is moving at 100 miles per hour, your true speed relative to the solid ground outside is 103.
Right, because you add them together.
Mainstream physics discarded the idea of an absolute ground for the universe. But the author argues that Maxwell's electromagnetic field is that ground. So the Earth's true speed isn't just 1/10,000th of the speed of light.
It is our orbital speed plus the sun's velocity through the EM field, velocity alpha.
You got it.
Here's where it gets really interesting. Because if you accept that there is an absolute EM field and we are moving through it at velocity alpha, the author claims you completely solve one of the weirdest ideas in modern physics.
Lorentz contraction.
Yes, Lorentz contraction.
Which is the mainstream idea we touched on earlier.
Yeah.
That as an object gets closer to the speed of light, it literally physically compresses in the direction it's moving.
Right. So a 100-foot spaceship flying near the speed of light physically shrinks to 50 feet long from the perspective of someone watching it.
Which is wild to think about.
And the author explicitly mocks this. They have this great line about scientists believing an object physically shrinks into a banana shape or gets a banana face.
A banana face.
Yeah. To the author, the idea that matter, which is mostly empty space held together by atomic forces, would physically squish down into a flat plane just because it's moving fast is absurd. They argue things don't physically squish at all. Instead, they just look distorted to the observer.
And why do they look distorted? Because of the information delay of light traveling through that absolute EM field. The light from the front of a fast-moving object reaches your eye at a different time than the light from the back.
The author insists it shouldn't be a physical Lorentz contraction. It should be a Lorentz correction equation.
Correction, right.
It should be an equation used by the umpire to just correct the corrupted visual data, not a theory that claims the actual physical matter of the universe is shrinking like a crushed soda can.
This raises an important question, though. If things aren't actually shrinking into a banana shape, what are they doing? If we use the umpire's math to correct for the delay, how does a fast-moving object actually appear?
The text actually gives us a name for this exact visual effect. It introduces a concept called the Penrose-Terrell rotation.
Yes, this was proposed independently by physicists Roger Penrose and James Terrell back in 1959.
Okay, walk us through it.
Imagine you have a solid cube moving past you at 99.99% the speed of light. Under strict Lorentz contraction, you'd expect it to look flattened into a pancake.
Right, squished flat.
But Penrose and Terrell proved that's not what you would actually see. Because the cube is moving so incredibly fast, the light emitted from the far back edge of the cube takes slightly longer to reach your eye than the light from the front edge.
Because the cube is basically outrunning its own light.
Essentially, yes.
It's moving so fast that by the time the light from the back edge finally hits your retina, the cube has already moved significantly forward in space.
Exactly. Your brain ends up processing the delayed light from the back of the cube at the exact same moment it processes the fresh light from the side of the cube.
Oh, weird. So what is the visual result?
You see the front, the side, and the back of the object simultaneously. It doesn't look squished. It looks like it is rotated to face you.
It's a massive optical illusion happening at the speed of light.
It really is.
But, true to form, our author doesn't just accept Penrose's theory wholesale. They acknowledge Penrose was an absolute genius, but they claim he made a slight error. The author says Penrose stopped 0.01 step short of the ultimate truth.
The author's critique is that Penrose still treated the mathematical space as physical space. He figured out the optical illusion, which was a huge step, but he didn't fully embrace the role of the external, absolute electromagnetic field.
He didn't take the umpire's view.
Right. He didn't view the moving cube from the perspective of Liu Bang, the umpire at z=100, looking down at the whole system moving through a physical medium.
Which leads us to a turning point in the source material. The author describes their 2004 aha moment. This was when they applied this umpire top-down perspective to one of the most famous, brain-breaking setups in all of quantum mechanics.
The double slit experiment.
The double slit experiment.
For context, the double slit experiment is usually viewed from a static, head-on perspective. You fire a single electron at a solid wall that has two tiny slits in it.
And standard quantum mechanics says the electron acts like a probability wave, right?
Exactly, passing through both slits at once and creating an interference pattern on the screen behind it. It's the absolute cornerstone of wave-particle duality.
Right, but the author says, no, float up to z=100. Look at the experiment from above as the umpire.
A totally different perspective.
And they bring in this incredibly vivid detail. They argue that when you fire that electron toward the slits, it is not happening in a pristine, empty mathematical void. The electron is a physical object moving through a physical medium, the EM field.
To explain this, the author compares the electron to an airplane flying through a Kármán vortex.
A wake turbulence. Anyone who has been on a bumpy flight near an airport knows exactly what wake turbulence is.
Exactly. When a plane flies through the air, it leaves behind invisible, chaotic, swirling eddies of air, a wake that the next plane has to fly through.
It's basically rough air.
Right. A Kármán vortex street is a repeating pattern of swirling vortices. The author argues that the electron is flying through the actual gravitational and electromagnetic wake left behind by the atoms of the slits themselves.
And by all the previous particles that were fired before it?
Yes. The absolute EM field is literally churning.
The author claims standard physicists view the double slit experiment purely mathematically. They draw clean probability waves on a chalkboard.
But they completely ignore the actual physical airspace.
Yes, the turbulent, swirling EM field that the particle must traverse. The electron isn't magically splitting into two probability waves. It is physically getting buffeted left and right by the historical wake of the universe itself.
If we connect this to the bigger picture, the entire thesis of this incredibly dense, highly unconventional blog post really boils down to one foundational warning. The map is not the territory.
And we forget that all the time.
We really do. Our Cartesian grids, our clean XYZ axes, our perfectly balanced mathematical formulas, they're just abstract models. They're umbrellas we hold up to try and make sense of the storm.
That's a great way to put it.
The author is practically begging us not to forget the physical reality of the electromagnetic field and, most importantly, the sheer inescapable physical time it takes for a single photon of light to travel from an event to our eyeball.
Right.
If you ignore the delay, if you ignore the abstract capacitor holding the data, you mistake an optical illusion for a shrinking universe.
So what does this all mean for you, listening right now? Why does a dense critique of Einstein, using ancient Chinese generals and airplane sensors, actually matter to your daily life?
It's a fair question.
Because whether you are a physicist looking through a telescope at a distant star, a day trader analyzing a stock market trend on a glowing screen, or just a person trying to resolve a miscommunication with a friend, you are always operating on a slight delay.
Always.
Information takes time to travel across space, it takes time to be processed by machines, and it takes time to be understood by the human brain. You are never, ever seeing now.
Never.
You are always processing a chaotic collage of different pasts, trying desperately to sync them all up with an abstract capacitor in your mind.
Every single one of us is just trying to be Liu Bang. We're all trying to be the umpire sitting in the high chair, trying to reconstruct a fair, accurate map out of chaotic, delayed signals.
Which leaves me with this final, lingering thought for you to chew on long after we wrap up today. If everything we perceive, literally everything we see, hear, and measure, is just an information-delayed illusion.
The map, not the territory.
Right. And if our physical laws and mathematical models are just umbrellas shielding us from that temporal chaos, what would it actually look like if we could somehow step outside the universe?
Oh, well.
If we could transcend the electromagnetic field entirely and see the true absolute now all at once without any delay whatsoever, would the universe look like a perfectly ordered tennis court or something entirely unimaginable?